In this video, we'll be discussing the term conjugate acid-base pairs, giving an example of what they are and how you can determine what component is the acid, which component is the base, and its conjugate acid and base pair by looking at a balanced chemical equation. As we have said in some of the previous videos, for general chemistry, we're primarily interested in the Bronsted-Lowry acid-base theory, which states that an acid is a proton donor and a base is a proton acceptor. One of the advantages of the Bronsted-Lowry theory is that it illustrates the reversibility of a lot of our reactions. So if we have a generic example of some acid, right, over here, that donates a proton, in that case this proton here, is donated to the base, yielding the same acid group, which is now missing that hydrogen, and a base which has now picked up the hydrogen. So the original base now has an extra hydrogen after the reaction. So if we were to do the reaction in reverse, go in the reverse direction, this base would be the one that is donating the hydrogen atom. So it would be acting as the acid in the reverse direction. In the original reaction, the thing that started out as the acid now has a lone pair of electrons, right? Because when it donates the proton, it donates it as an H+, which leaves behind a pair of electrons. So we have a lone pair here, which is the key component to a Bronsted-Lowry base. So the original acid, which now has a lone pair of electrons after the reaction takes place, it can now act as a base in the reverse process. So if we take the reaction that we had up top, reverse it, so now we have our products are now our reactants are now our products. You can see that the ion of the acid that we started out with is now acting as the base. Right? It has this lone pair of electrons here. These can accept a proton to give HA. And HB+, right, which came from the base in the first reaction, is now donating that proton to A-, leaving B all by itself. So in this case, initially we had HA. In our first reaction, this was acting as an acid. B was acting as the base. In the reverse process, this A is acting as the base, and HB is acting as the acid. So what we do is we say that in the reverse direction, this A- is our conjugate base, and HB is our conjugate acid. We can actually pair these up by looking at which things went down in the of hydrogen atoms. So we have here, we have our acid and its conjugate base. They come in pairs. On one side you have an acid, on the other side the remainder of that molecule, less the hydrogen, is the conjugate base. Here we have the base pairing up with what we will call the conjugate acid. So the base on the reactant side picks up a hydrogen to become the conjugate acid. All the conjugate term means is that when you put the reaction in the reverse direction, that part becomes either the acid or the base. So you have your acid here forming its conjugate base. If we run the reaction in reverse, what's left over after the acid donates its hydrogen here is something that, going in the reverse direction, is going to act like a base. So we have what we will call conjugate acid-base pairs. You have its acid and its conjugate base. The acid will be always on the reactant side. It gives up or donates a proton to become the conjugate base on the product side. So the original acid and base are what will be on the reactant side. The conjugate is the component that will be on the product side. So if something picks up a hydrogen atom or picks up a proton, it acts as a base on the reactant side, and its pair on the product side is the conjugate acid. If something acts as an acid on the reactant side, i.e. it gives up a hydrogen, then on the product side, what remains is called the conjugate base. So in the Bronsted-Lowry acid-base reaction, the original base becomes an acid in the reverse direction, and that acid we call the conjugate acid. The original acid becomes a base in the reverse process, and we call that base a conjugate base. Each one of them will have a pair. The acid is paired with the conjugate base. The base is paired with the conjugate acid. In an overall reaction, what this would look like is we have our ammonia ion. It's going to act as a base by picking up a hydrogen from water, which will act as an acid. So on the reactant side, the nitrogen is going to be picking up a proton. It will be accepting a proton, coming over here to form the ammonium. So the base on the reactant side is paired with the conjugate acid. The difference between the two is just that the conjugate acid has one more hydrogen than the conjugate base does. You also have the acid and its conjugate base. So water donates a proton to the ammonia. The result is the hydroxide ion, OH-, which is the conjugate base to the acid. Right? So the difference between the two is that the conjugate base will have one less hydrogen or one less proton than the acid that it came from. So a base accepts a proton to become a conjugate acid, and the acid donates a proton to become the conjugate base. Generic examples would be anything that has a hydrogen reacting with something else. What acts as an acid is going to lose that proton. Its charge will go down or become negative. So we're left with, it started out on the reactant side as neutral. So over here it will go down. So it will become more negative, A-. And the base will pick up that proton, will accept the proton to become HB+. One of the key parts is that the charge is maintained, the overall charge on both sides. So if you add up the charge on the left, 0 plus 0 gives you a 0 overall charge on the left. On the right, -1 plus a +1 gives you 0. Here you have your acid. That means that we can connect it with this one because the A remains the same. Because this now has one less proton, this is our conjugate acid. And this, because it has picked up a proton compared to the base, this is our conjugate base. Now, if you're ever asked to figure out the conjugate, sorry, this is the acid is paired with its conjugate base, and the base is paired with its conjugate acid. If you're ever asked to figure out which one is an acid and which one is a base, or if you're ever asked to figure out the conjugate base from an acid, the way you do that is you just remove one of the acidic protons. So let's say we have H2SO4, and you're asked to determine what the conjugate base of this would be. So all we have to do is find our hydrogens and remove one. So that would be H1SO4, and because we gave up a proton, to maintain charge balance, this would have to have a negative charge on it. If we had something like ammonia, NH3, and it were to act as an acid, ammonia is another example of an amphoteric substance, meaning that it can act either as an acid or as a base. Right, so we have ammonia. If it acts as an acid, it loses hydrogen. So we are producing a proton or a hydrogen ion. And so our nitrogen will have one less hydrogen. To maintain charge balance, this has to have a negative. Okay. We can also look at how we're going to do this for bases. So let's take the example of ammonia again. And this time, it's going to work as a conjugate base. So it will pick up a hydrogen from some acid, becoming NH4. And to maintain charge balance, this side here has a plus, and so this will have to be a plus. Right? So the conjugate base would be NH4+. Let's say we have another base like CH3COO-, the acetate ion. The conjugate pair would be we take our base and we just add a hydrogen to it. So this would be CH3COOH, right? So because it picked up a proton to become acetic acid, right? So the way you will be able to determine the acid-base pairs from an acid or a base is if you're trying to find the conjugate base to an acid, just remove a hydrogen and write out the formula. To come up with the conjugate acid, you just add a hydrogen to the molecular formula.